In this section, we are going to look at directional derivatives. So let's start by considering some function f of xy. Now, we've learned how to take partial derivatives of a function, right? We know how to take the partial derivative of f with respect to x. We know how to take the partial derivative with respect to y. And what these do, they give us the rate of change of function f in the direction of these variables. Rate of change of f in direction of positive x. And this tells us the rate of change of function f in the direction of positive y. Okay? So graphically, what we're doing here is, if we have some point, we hold x fixed, we look in the positive y direction, and then we take the derivative of the curve at the point, right? Or if we want the rate of change with respect to x, then we hold the y value fixed. We look at how that curve changes let me turn it the way that we would be used to saying it. As we move in the positive x direction, how does the function change? How does that curve change? And that tells us how the surface changes in that direction, right? But there's nothing special about the x or the y directions. Why do I have to only look in those directions to take a derivative? What if I look in some other direction? There's lots of directions I can look in. Can I find a derivative in any of those directions? Can I take a curve in one of these directions, maybe this curve here, and then look at how the function changes as I move along that curve at a point? Okay, so that's what we're going to be doing in this section. So how can we find the rate of change of function f at some point, let's call it r naught, and just two components, x naught, y naught, in the direction of some vector v. Okay, how do we do that? All right. So we call this a directional derivative. And we notate it dvf. Okay, the directional derivative of function f in this direction, in the direction of that particular vector. Okay, so how do we actually go about doing that? Well, with the partial derivatives, with our partial derivative of f with respect to x, with the partial derivative of f with respect to y, we're restricting ourselves to one direction, right, along one line. If we want to see how f changes in the positive x direction, we hold the y fixed. We only let the x change, right? If we want the rate of change in the positive y direction, we hold the x fixed. We look in the direction where the y changes. So we want to do the same thing here. We want to hold everything fixed, but we want to look in a particular direction and only change the value of the function in that direction. In this case, we want to look in the direction of vector v. So our strategy here is to evaluate function f, but only in a particular direction. And we're going to find a vector valued function that traverses that direction. Okay? So we evaluate f along a vector valued function in the desired direction. And then if I can find that, then I can take the derivative of it, and that will give me my directional derivative. Right? But I need to find a vector valued function in the direction I want. So if I want to move in the direction of a vector, if you think about it, if I'm moving in the direction of a vector, that means I'm moving in a straight line, right? So let's construct this vector valued function. And we got to be careful here, as we'll see. But we know we want a line. We're interested in particularly the vector valued function, or I'm sorry, the rate of change at this point. So we know we want to pass through that point. So that will be a point on the line. And then plus t times a direction vector. I want to see how things change as I move in this direction. And so plus t times the direction vector. That is a line that passes through the point I'm interested in and moving in the direction I'm interested in. Except this isn't quite right. It's just about right. It does traverse the path I want, but as we've learned, there's lots of ways that we could traverse a particular path using a vector valued function, right? If I take, instead of v, if I do 2 times v, that will traverse the same path, but now it's going twice as fast. If you're going twice as fast, then for the same amount of change in t, you're now changing function f twice as fast. Your derivative will be twice as fast. Okay? So what we want is we want to find some standardized way to traverse this path. Okay, some standard speed to go at. If you remember when we covered arc length parameterization, we found a way to standardize how we talk about a vector valued function, a standard way to traverse the curve so that the parameter also corresponds to how far we've traversed it. And that's what we want here. That's what we do up here, by the way. If I plug in x equals 1, I've gone from my point 1 unit away, right? 1 unit away from the origin. If I let y be 2, I know I've gone a distance of 2 from the origin. The number I plug in corresponds to the vertical distance or the horizontal distance, right? I want the same thing here. I want the t I plug in to correspond to how far I have moved in the direction of vector v. Okay, so how do I do that? I end up needing to normalize vector v. I need a unit vector. Since if I use a unit vector, then if I plug in 1 for t, I'm moving I'm moving 1 unit vector away from my initial point r0. Okay, 1 unit vector has length 1, so I'm moving length 1 away. So this is an arc length parameterization, and it standardizes how fast we move along the trajectory. So we don't have to worry about whether we're going faster or slower. By using a normalized unit vector here, make sure that we are traversing the trajectory at the right speed. We're going over the surface at the right speed. Okay? So now we are looking at function f, and we're evaluating function f along a particular trajectory. Okay, so we've restricted ourselves to a single line. What we want to do now is we want to take the derivative of that line. We want to see how f changes as we move along this line. So actually I won't use that quite yet. we want to know how function f changes as we move along this line, which is exactly what the derivative tells us, the rate of change of f as we change t. Now this looks familiar. Where have we seen this before? We saw this just in the last section, right? If we're plugging a vector-valued function into a multivariate function, we can take the derivative using the multivariate chain rule. Okay, so according to the multivariable chain rule, you start by taking the gradient of the multivariable outer function, and then I'm going to take the dot product of that with the derivative of the vector valued function on the inside. Okay, so that gives me how much f is changing in the direction of r, okay, as we move along that path. All right, so let's plug in what we know. We have r of t right here. We're going to need r prime of t, so let's calculate that. R naught is a vector, but just a constant vector. So when I take the derivative, it'll just go to 0. T times v over norm of v, that's just, t is my variable, and then v norm of v is just a constant vector. So t times a constant, if I take the derivative, the derivative of t is just 1, and I just get the constant. So I'm just going to get vector v over norm of v. And that's my derivative, just the unit vector pointing in the direction I want my derivative in. Okay, so if I plug in, I get r of t, which is r naught plus t times v over norm of v. And I take the dot product of that with r prime, which is just v over norm of v. All right, one more thing. I'm interested in this derivative at a particular point, right? Specifically when r naught is equal to some particular point x naught, y naught. I reach that point r naught when t equals 0. So r of 0 equals r naught. Since I'm interested in the rate of change at r naught, I want to plug in t equals 0 so I can find the rate of change when I'm plugging in that point into f. So if I just plug in t equals 0, if I plug in t equals 0 here, this just goes away, right? That would just go to 0, and I just have r naught. So gradient of f at r naught. And then this, there's no t over here, so that just stays the same. And what we just did is we found the directional derivative of function f in the direction of vector v evaluated at the point r naught. Okay, that's what we found. And so we could summarize this into a formula for the directional derivative. The directional derivative of some function f of xy in the direction of vector v is generally going to be given by the formula where we take the gradient of f and take the dot product with the unit vector pointing in the direction of the vector we're interested in. Okay, notice for any xy we want, we just plug in. Just like if we wanted any point here, we could just plug it in here. This works for any point we're interested in. So this is the formula we are going to use to find the directional derivative, the rate of change of function f in whatever direction we want to look. So let's take a look at a couple of examples. Here, we want to find the directional derivative of function g at a particular point, q equals 1 comma pi over 4, in the direction of vector u. How much is function g changing in the direction of vector u? Okay, so we know the directional derivative of function g in the direction of vector u is going to be the gradient of function g dotted with a unit vector pointing in the direction of u. We need to normalize vector u. So we just do the calculation. So let's start with the gradient of g. The gradient of g, I'm going to first take the partial derivative with respect to x. If I take the partial derivative of the function with respect to x, I take the derivative of e to the x, which is just e to the x, and then sine of y I treat as a constant, so it just comes along for the ride. And then the second component would be the partial derivative with respect to variable y. If I take the derivative with respect to variable y, derivative of e to the x, well, that's just a constant with respect to variable y, so I'm going to just let it come along for the ride. And then derivative of sine of y is cosine y. Okay, so that's my gradient. And then I'm also going to need to normalize vector u. Okay, so u over norm of u is going to be the vector 4 comma negative 3 divided by square root of first component squared plus second component squared. Okay. In the denominator, 4 squared is 16, negative 3 squared is 9. 16 plus 9 is 25, and the square root of 25 is 5. And so I end up with 4/5 comma negative 3/5. Okay, I have the pieces I need. Let's plug in. I'm going to get gradient of g, that is e to the x sine of y, comma, e to the x cosine of y. I'm going to take the dot product of that with the unit vector pointing in the direction of vector u, which is 4/5 comma negative 3/5. And so I get, just multiply corresponding components, I get 4/5 e to the x sine y minus 3/5 e to the x cosine y, just taking that dot product. Okay? So that is the general form for a directional derivative in the direction of this particular vector. Now I can plug in any x, y point I want, and it will tell me the rate of change of function g at that point in the direction of vector u. In particular, I'm interested in the point 1 comma pi over 4. So let's plug that in. And so I get 4/5 e to the x, so e to the 1, sine of pi over 4, minus 3/5 e to the x, so that's e to the 1, cosine of y, so that's cosine of pi over 4. Now, sine and cosine of pi over 4, there's a good chance you remember what those are, but if you don't, just draw a triangle. Pi over 4 is 45 degrees, so I'm going to get a 45, 45, 90 triangle in the first quadrant. Ratios of the sides of a 45, 45, 90 triangle are 1, 1, root 2. And so cosine of pi over 4 and sine of pi over 4 will both be 1 over root 2. Adjacent over hypotenuse and opposite over hypotenuse. Right, so we get 4/5. E to the 1 is just e. Sine of pi over 4 is 1 over root 2. Minus 3/5. E to the 1 is just e. And cosine of pi over 4 is also 1 over root 2. So what I'm going to do is I'm going to factor out what I have in common. and there's quite a bit I have in common. I have an e in common. I have the 5 in the denominator in common. And I have the root 2 in the denominator in common. And then the 1 in the numerator, you could just stick it by the e if you want, but 1 times e is just e. Okay, that leaves me, once I take all that out, with a 4 here and a 3 here. So 4 minus 3. 4 minus 3 is just 1, so my final answer is e over 5 square roots of 2. That's the rate of change of function g at the particular point 1 comma pi over 4 in the direction of vector u. Okay? All right. Let's do one more. Here we want to find the directional derivative of a 3-variable function at a particular point in a particular direction. Even though it's a 3-variable function, the process in the formula is exactly the same. So I want the directional derivative of function f in the direction of vector u. So I need the gradient of f dotted with the unit vector in the direction of vector u. So let's start by finding the gradient of f. I should have 3 components for this gradient, right? 1 derivative for each of the 3 variables. Derivative with respect to x is going to be just z. Derivative with respect to variable y is 2y. And derivative with respect to variable z is x. Okay, this is the gradient of f. And now I need to find a unit vector pointing in the same direction as vector u. So vector u, and then I normalize it to turn it into a unit vector. I divide by its norm. I get the point 2, negative 1, 2, or the vector rather, 2, negative 1, 2, and divide by first component squared plus second component squared plus third component squared. I'll leave the numerator the same for now. In the denominator, 2 squared plus 1 squared plus 2 squared, that's 4 plus 1 plus 4, that's 9. Square root of 9 is 3. So I get 2/3, negative 1/3, 2/3. Okay, so let's plug those in. Gradient function right here. I get z 2y x. I'm going to take the dot product of that with the unit vector pointing in the direction of vector u, and that's 2/3, negative 1/3, 2/3. 2/3, negative 1/3, 2/3. I'm going to take the dot product, so I'm going to multiply corresponding components and add them all together. So first component times first component, I get 2/3 z. Second component times second component, I'm going to get negative 2/3 y. And last component times last component, I get 2/3 x. Okay, that is the general formula for the directional derivative of function f in the direction of u. Now I can plug in any point I want, and it will tell me the directional derivative of function f in that direction. So just plug in the point, right? I'm interested in the directional derivative in particular at the point 1, 2, 2. Let's plug that in. So I'm going to plug in 2 for z, 2 for y, 1 for x. 2/3 times 2 minus 2/3 times 2, those will cancel. And so I just get 2/3 times 1, which is just 2/3. So that's the rate of change of function f in the direction of vector u at the point. That means at that particular point, at that particular moment, if you are moving in the direction of vector u, for every 1 unit you move in that direction, your function value is changing by 2/3. Okay? So now with these directional derivatives, we can find the rate of change of any function f in many, many directions. So a natural question that arises might be, in which of those directions does function f increase the fastest? In which direction is the rate of increase, the rate of change, the fastest? And how fast in that direction does it increase? Okay, so we can answer this question using the directional derivative. So the formula for the directional derivative, and in the direction of some vector u, we're going to take the gradient of f, and we take the dot product with a unit vector in the direction of vector u. Okay? Now, what we're going to do here is we're going to use one of our properties of dot products. Recall that if I have two vectors, a and b, and I take their dot product, one of the properties is that this is equal to the magnitude of a times the magnitude of b times cosine of the angle between those two vectors, right? So that's the property we're going to use here. Here our two vectors are the norm of f and the unit vector pointing in the direction of u. Okay, so if I use that property, I'm going to get the norm of vector f, the gradient of f times the norm of u over norm of u times cosine of the angle between them. So what we want to do is we want to use this way to formulate the dot product. Think about what direction would we have to point for f to increase the fastest? What would theta have to be, right? Theta is going to tell us what direction we would have to be relative to the gradient of f. Okay? So first off, vector u over norm of u, we specifically chose that to be a unit vector. So this should just be 1, right? The length of this vector is just 1. And then the gradient function, at any given point, the gradient is just a constant value, right? At different points, of course, it'll change, but we're looking at what's the fastest rate of increase for any particular point that we're focused on. So we're focused on a particular point, which means that this directional derivative is going to be maximized at the same time cosine of theta is maximized, when cosine of theta is biggest. So when is cosine theta biggest? What is the biggest value cosine can take on? Well, it'd be 1, right? So this is largest when cosine is equal to 1. And if we limit ourselves to an angle where theta is between 0 and pi, then that means theta would have to be 0, right? Cosine of theta equals 1 when theta equals 0. Which means that our directional derivative is largest. Our rate of change of function f is largest when the angle between the gradient and this unit vector are 0. In other words, it's largest when this unit vector is pointing in the direction of the gradient. The gradient is already pointing in the direction where f changes the fastest. So function f increases the fastest at any particular point in the direction of the gradient at that point. Okay? So great, we know the direction where function f increases the fastest. Just happens to be the same direction the gradient is pointing. But how fast is that rate of increase? Okay? How much is the directional derivative in that direction? Okay? Well, the directional derivative in that direction, when theta equals 0, that will be the magnitude of the rate of increase, right? The size of that directional derivative is how fast f is changing. And we decided that it changes fastest when theta equals 0, when cosine of theta equals 1. So that directional derivative when cosine of theta equals 1, if this is 1, then that directional derivative is just going to be equal to the norm of the gradient of f. So the length of the gradient, the norm or magnitude of that gradient, is the rate of change of where that f is changing when it is pointing that direction. It is how the fastest amount f changes at a point. So also, the norm of the gradient is the fastest rate of change of f at a point. It is how fast f is changing if you go in the direction of fastest increase. Okay? Similarly, we could also ask, in what direction would f decrease the fastest? Would the rate of change shrink the fastest? And we use the same argument. This is still always equal to this. Okay, so this would have the smallest value when this reaches a minimum, when cosine of theta reaches a minimum, since the norm of the gradient would be held constant at any point. Cosine of theta reaches a minimum, the lowest value cosine of v could be is -1. And that happens when the angle is pi. So that would happen when the direction we're pointing in is exactly opposite to the gradient of f. Okay? Also, f of xy decreases the fastest in exactly the opposite direction. In the direction of, if I want to point exactly the opposite direction, I just take that vector and throw a negative in front, right? That just points it in the opposite direction. And it kind of makes sense, right? If you're looking at just a single point and you're looking at the place where the surface is steepest, where at that exact point is it going to also be steepest going down? In the exact opposite direction, right? So using the directional derivative, we can see in which direction is the surface increasing the fastest, is the function increasing the fastest, and which direction is it decreasing the fastest. It increases the fastest in the direction of the gradient. It decreases the fastest in the exact opposite direction, in the direction of the negative gradient. Let's do a quick example. We want to find the maximum rate of change of this function at the 0.52. So based on what we just discussed, the gradient of f, this points in the direction of the maximum rate of change. That's the direction I would want to go if I want function f to increase the fastest. If we're dealing with the surface, that's the direction I go if I want the surface to grow as quickly as possible. It's where I would have to walk the steepest going uphill. Points in the direction of the maximum rate of change. Okay? And the norm of that gradient, the norm of the gradient tells me how much that rate of change is. Okay, so if I'm climbing up a mountain, And the mountain is the surface. F of xy tells me the height at every point. For any particular point, if I find the gradient of that function, it tells me where I should walk to where the mountain's going to be steepest. Okay? And the norm of the gradient tells me how steep it is in that direction, where it is and how steep it is. Okay? In this case, we want to know how steep it is. We want the actual maximum rate of change, not the direction of it, but the actual maximum rate of change. So I'm going to want the gradient, and I'm going to want to find the norm of the gradient to find the maximum rate of change at the 0.52. Okay, so let's start by finding the gradient of f. Partial derivative with respect to x. 2y to the fourth I'm going to treat as a constant. So it just comes along for the ride. Let's see. It's write it as a vector. 2y to the fourth I treat as a constant. It comes along for the ride. An x in the denominator I could think of as x to the negative 1. If I take the derivative using the power rule, I could get negative x to the negative 2. Okay, and that's my partial derivative with respect to x. Partial derivative with respect to y. The 2 and the x I'm treating as constants. So I can treat that 2 over x as a constant coefficient. And then the derivative of y to the fourth is 4y cubed. And so fully simplified, I get negative 2y to the fourth over x squared for my first component, and 8y cubed over x for my second component. Okay, I'm interested in what's going on specifically at the 0.52. So let's plug that in. So if I plug in 5,2, I get negative 2 times 5 to the fourth divided by 2 squared, comma, 8, oh wait, sorry, mixed up my x and y. Okay, y is 2, x is 5. That's going to be a little bit easier to calculate. Okay, and then for the second component here, plug in 2 for the y and 5 for the x. So the first component is 2 to the fourth is 16 times another 2 is 32. And then 5 squared in the denominator is 25. So my first component is 32/25, comma, and my second component here is 8 times 2 cubed. 2 cubed is also 8, so 8 times 8 is 64 divided by 5. Okay, now that is the direction where the function increases the fastest at the 0.52. I want to know the actual maximum rate of change. And so I'm going to take the norm of it. Give myself a little more room here. The norm of the gradient. Okay, so that's going to be square root of my first component squared plus my second component squared. Now, plugging this into a calculator is probably a good idea. We could actually do a fair bit of simplifying, though, without a calculator. Okay, so if I wanted to do this without a calculator, I notice there's a lot of repeated factors here that I'll be able to factor out. So first off, negative squared goes away. So I'm going to get 32 squared over 25 squared. I'm not going to bother to try to square those just yet. And then here, 64 I know is 2 times 32. And that's part of the reason why I'm thinking maybe I don't need a calculator here. 2 times 32, and I'm going to square both of them. In my denominator, I have 5 squared, that's 25. Okay? And so I see that if I look at the common factors here, I have a 32 squared in the numerator of both of these fractions. And I have a 25 in the denominator of both of these fractions. And if I take that out, so I took the 32 squared out, leaving me just the 1 in the numerator of this first fraction. And I took one of the 25s out, leaving me 125 in the denominator of that first fraction. For my second fraction, I took the 32 squared out, leaving me just 2 squared in the numerator. And I took the 25 out of the denominator, so I just have a 1 down there. Okay. Square root of 32 squared is just 32. The square root of 25 is 5, so I can pull those out of the root. And in the root, I still have 1 over 25 plus 2 squared over 1, that's 4. Okay. 4 is the same thing as 100 over 25. I'm going to get 32 over 5 times the square root of, so this is 100 over 25. If I add the two fractions together, I get 101 over 25. Square root of 25 is 5 times the 5 that's already down there. I'll get 25 overall, and then I still have the root 101, which there's not much I could do about without a calculator. And so without a calculator, that's the answer. If you want a decimal approximation, you could pull out your calculator for that. Okay, so that is how fast the function changes at this point, where it is increasing the fastest. That is the maximum rate of change. That is how fast it is moving in the direction of the gradient, in this direction. Okay? Let's do just one more example together. This example is a little different. We have a function. We want to find a unit tangent vector to the level curve at the point 4, 2. All right? So just as a reminder what level curves are, if I look at several level curves, I'd get a sort of contour plot, right? And a level curve is one of the lines in these contour plots. Recall that a level curve is the curve we get by setting f of xy equal to some constant. Okay, we're looking at that particular level where the function value is equal to a constant. So in particular, what does that mean for the derivative? We want a unit vector, unit tangent vector to the level curve at the point 4, 2. So suppose u is the unit tangent vector to the level curve at point 4, 2. Okay, then let's look at the directional derivative in that direction. So this would be the gradient of f, which I haven't found yet, but we could find that in a moment, dotted with this vector u, and I've already assumed it's a unit vector, so I don't have to normalize it. It already has length 1. Okay, now what should this be equal to? Well, we're pointing in the direction of the level curve, right? So maybe this is our point right here. So let's say this is our point right here. And we're pointing in maybe this direction. We're tangent to that level curve. That's what we're looking for. In that direction, how much is function f changing? Well, if this is a level curve, then f is constant along the level curve. So if I'm pointing in the same direction the level curve is going, if I'm pointing tangent to the level curve, then at that exact moment, in that exact direction, function f shouldn't be changing at all. The derivative should be 0, right? The unit tangent, or the directional derivative should be 0. What does it mean when the dot product of two vectors is 0? It means that the two vectors are orthogonal, doesn't it? So just to summarize, f is constant along the level curve. So there's no change in this direction. There's no change of function f in the direction of u. Okay? And I know that the u I'm looking for, the vector I'm looking for, dotted with the gradient, is going to be 0, which means these two have to be orthogonal. Remember, the dot product of two vectors is 0 if and only if the vectors are orthogonal. So what I want is I want to find a vector that is orthogonal to the gradient. I want to find a vector so that their dot product is equal to 0. Okay, and then I want to make sure it's a unit vector. If I find a vector that is orthogonal to the gradient, then it will be tangent to the level curve. Okay, kind of makes sense, doesn't it, if you think about it? Because the gradient is the direction where the function increases the fastest. So maybe the function is increasing the fastest going this direction. Okay, it generally increases. If you want to increase the fastest, you want to get away from this constant level as fast as you can. Okay, you want to get away from that constant value as fast as you can. That level curve is where everything's constant. You want to increase as fast as you can. So you want to get away from it as fast as you can. You get away from it by moving orthogonal to it. So the gradient vector is going to be normal or orthogonal to a level curve. And that means that the vector tangent to the level curve is going to be orthogonal to the gradient. Okay? So our strategy here is to find the gradient and then find a vector orthogonal to that gradient. And you'll see it's actually going to be pretty easy once we find the gradient. Okay? So let me just copy this down here, just so we can reference it. Okay, so I need the gradient of f. So I'm going to take the partial derivative first with respect to x. This is just a polynomial, so it's a pretty straightforward derivative, a lot of power rules. I get negative 10x plus 2y. Derivative of negative 4y squared is 0. Derivative of 5x is just 5. And then the derivative of 3y and 2 with respect to variable x is just 0. So that's my partial derivative of f with respect to variable x. Now I look at the next partial derivative with respect to variable y. Derivative of negative 5x squared with respect to y is 0. Derivative of 2xy is 2x. Derivative of negative 4y squared is negative 8y. Derivative of 5x is 0. Derivative of 3y is 3. And derivative of 2 is 0. So there's the gradient of f. I'm interested in particular in what this gradient is doing at the point 4, 2. I'm going to plug that in. So gradient of f at the point 4, 2. So I just plug in 4 for x, 2 for y. And I get For the first component, negative 40 plus 4 is negative 36. 5, negative 31. Okay. For the second component, 8 minus 16 is negative 8. Plus 3 is negative 5. All right. Now what I want is a vector orthogonal to this. So I want it so that a gradient of f dotted with this vector, I want it to be orthogonal. I want it to be equal to 0, right? So the gradient of f at the point is negative 31 comma negative 5. And let's say the components of vector u here are u1 comma u2. Okay. So if I take the dot product, I get negative 31 u1 minus 5 u2. The easiest way to find a vector that's orthogonal to a two-dimensional vector is just choose u1 and u2 so that the values are the opposite of what we have here. So I'm going to make 31u2. I'll take 5 to be u1, and then just make sure that these two guys have opposite signs. I'm going to choose u1 to equal 5, and I'll choose u2 to equal negative 31. Okay? That will definitely make sure that this is equal to 0, right? Because in both cases, I get 31 times 5, 31 times 5. In this first case, I have a negative and a positive, so that's a negative number overall. In this case, I have a negative and another negative, so that's a positive number overall. So one will be negative, one will be positive, and they'll be the same magnitude. So I'll definitely, when I add them together, I'll definitely get 0. I also wanted that first component to be positive because in the instructions, I wanted a unit tangent vector to the level curve that has a positive x component. So I made sure I chose the x to be positive. Okay? So this vector, because it is orthogonal to the gradient, it means it is orthogonal to the level curve. I'm sorry, tangent to the level curve. Got a positive x component. We're almost done. There's just one thing we need to do. The instructions did say we wanted a unit vector. So we need to normalize this vector for our final answer. Okay? So our final answer, we're going to normalize it so we have a unit vector tangent to the level curve. So I get 5 comma negative 31 divided by square root of 5 squared plus negative 31 squared. Okay. Five squared is 25. 31 squared, that's almost like 30 squared, which is 900. But then you'd have to add, what, another 61, so 961. Okay. And then 25 plus 961 is 986. So my final answer, well, unless you want to throw it into a calculator, is 5 over square root of 986, comma, negative 31 divided by square root of 986. It's a unit vector. It's got a positive x component, and because it is orthogonal to the gradient, it will be tangent to the level curve at the point 4, 2.